A magnitude 7.7 earthquake has struck the Flores region of eastern Indonesia, bringing renewed attention to one of the most dangerous active fault systems in the Indonesian archipelago. The earthquake occurred at 21:58 UTC on August 14, 2026, equivalent to 5:58 in the morning local time on August 15. Its epicenter was approximately 68 kilometers, or 42 miles, north-northwest of Endi, and the United States Geological Survey placed the depth at about 10 kilometers, or 6.2 miles. A shallow earthquake of this size is capable of producing violent shaking, landslides, structural collapse, and tsunami waves, and that danger became immediately apparent across Flores. Why did this earthquake immediately bring back memories of 1992? Why is a fault hidden along the northern side of Flores capable of producing earthquakes comparable to those generated by much more famous subduction zones? And why does the latest magnitude 7.7 event deserve particular attention when another earthquake of almost identical size devastated the same broad region more than 3 decades ago? The answer lies in the unusual tectonic architecture of eastern Indonesia. Flores sits inside a region where major plates and smaller crustal blocks are converging, colliding, and deforming. The Flores Thrust is one of the structures absorbing that enormous compression, and its history shows that it can release accumulated strain through powerful shallow thrust earthquakes. The latest earthquake is especially significant because its magnitude sits extremely close to the magnitude assigned to the devastating 1992 Flores earthquake. Depending on the catalog and methodology, the 1992 earthquake has been reported as magnitude 7.7 or 7.8, with some scientific analyses placing it near magnitude 7.9. The current earthquake is magnitude 7.7. In other words, the two events belong to essentially the same magnitude class. That does not mean they produced identical ruptures or identical consequences, but it immediately establishes a remarkable comparison. A fault system responsible for one of Indonesia's deadliest 20th century earthquakes has now produced another earthquake of almost the same enormous scale. Flores belongs to the Lesser Sunda Islands, a chain stretching across one of the most complicated portions of the Indonesian plate boundary system. Far to the south, the Indo-Australian plate is moving northward toward the Sunda Banda region. In some areas, oceanic lithosphere is being forced beneath the overriding plate. Farther east, the tectonic architecture becomes increasingly complicated because the Australian continental margin approaches and interacts with the island arc. Instead of concentrating all deformation along one perfectly continuous boundary, the region distributes strain through multiple faults and thrust systems. The Flores Thrust is one of these structures, positioned north of the volcanic arc in what geologists call the back arc region. Back arc describes the tectonic position of the fault rather than its importance. The primary volcanic arc lies between the main subduction zone and the back arc region, but the crust behind that volcanic chain can still experience tremendous compression. In the Flores region, the continuing convergence between Australia and the Sunda Banda system has helped produce a major east-west oriented thrust system. The fault generally dips southward beneath the island and offshore areas, allowing one block of crust to move upward relative to another. That geometry makes the Flores Thrust fundamentally different from a simple vertical strike-slip fault. It is a compressional structure, and compression is precisely what allows large sections of crust to be shortened and stacked over one another during major earthquakes. A thrust earthquake occurs when rocks on one side of a fault are pushed over rocks on the other side. The movement can be measured in meters during a major earthquake, even though the long-term tectonic motion may accumulate at only millimeters or centimeters per year. That contrast is one of the most important concepts in earthquake science. For decades, tectonic forces can slowly deform the crust without producing a noticeable earthquake. Strain accumulates within locked portions of the fault until the rocks can no longer sustain the growing stress. A rupture then propagates through the fault, releasing stored elastic energy as seismic waves. The August 14 earthquake represents another major release from this long-running tectonic process. The reported depth of approximately 10 kilometers, or 6 miles, is especially important. Earthquakes at this depth occur close enough to the surface that seismic waves can reach communities with relatively little loss of energy compared with deeper earthquakes. When the earthquake is also magnitude 7.7, the result can be extremely intense shaking over a wide region. Reports from Flores indicate strong shaking across several districts, while buildings, homes, and public facilities suffered damage. Landslides also blocked roads and complicated emergency operations. The shallow depth therefore helps explain why a large earthquake beneath or near the Flores Sea could produce serious consequences on land despite occurring offshore. The human consequences have already made clear that this was not merely a geological curiosity. Initial reports changed as emergency crews reached isolated communities, but authorities reported dozens of fatalities, extensive structural damage, and thousands of people displaced or evacuated. Associated landslides obstructed transportation routes, including portions of the Trans-Flores Highway, while power and communication disruptions made it more difficult to determine conditions in remote areas. More than 100 public facilities were reported damaged in early assessments, while homes and other structures collapsed or suffered significant damage. The full impact is still being assessed because mountainous terrain, damaged roads, and continuing aftershocks can delay access to affected communities. The immediate tsunami concern was another reason authorities responded so quickly. A large shallow earthquake occurring offshore on a thrust fault is one of the classic conditions capable of generating a tsunami. When a thrust earthquake causes vertical movement of the seafloor, it can lift or lower the water above it. That displacement creates waves that spread outward through the ocean. The resulting tsunami can reach nearby coastlines within minutes, leaving very little time for formal warnings. Indonesian authorities therefore issued a tsunami warning following the August 14 earthquake. Later observations showed that the resulting waves were much smaller than the catastrophic waves of 1992, and the warning was lifted after monitoring indicated that a major continuing tsunami threat was not developing. The latest tsunami behavior provides an important lesson. Earthquake magnitude does not directly determine tsunami height. Two earthquakes with nearly identical magnitudes can produce very different tsunami waves because the amount of vertical seafloor displacement, the depth of the rupture, the fault geometry, and the location of the rupture relative to the coastline can all vary. Submarine landslides can also dramatically increase wave heights locally. Early reports from the August event indicated observed tsunami amplitudes generally below 1 meter at several monitoring stations, although later reporting identified a maximum observed wave around 1.61 meters, or roughly 5 feet, at Riung. These measurements were vastly smaller than the extreme run-up documented after the 1992 earthquake. The 1992 comparison remains unavoidable because that earthquake demonstrated the full tsunami potential of the Flores region. On December 12, 1992, a magnitude 7.9 earthquake struck near the northern coast of Flores. The International Tsunami Information Center reports that the earthquake generated a local tsunami that killed approximately 1,690 people and destroyed around 18,000 houses. The first tsunami wave reached parts of Flores within approximately 2 minutes, while the northern coast was affected within roughly 5 minutes. Those numbers demonstrate why local earthquakes are particularly dangerous. Communities closest to the source may experience strong shaking and then face a tsunami before distant warning systems can provide detailed information. The largest documented run-up from the 1992 tsunami was extraordinary. At Riung Kroko, a small village near the northeastern end of Flores, water reached approximately 26.2 meters, or about 86 feet, above normal sea level. The village was overwhelmed, and 137 people were killed there. Researchers have suggested that offshore landslides triggered by the earthquake may have contributed to the unusually large waves. That possibility is important because it demonstrates why tsunami hazard in Indonesia cannot always be estimated from earthquake magnitude and fault displacement alone. An earthquake can destabilize the seabed, and a submarine landslide can then displace additional water and amplify tsunami waves in ways that are difficult to predict immediately after the earthquake. The 1992 disaster killed more than 2,000 people when earthquake and tsunami impacts were combined, according to historical assessments. Maumere and Bobby Islands suffered especially severe losses, while large numbers of buildings across Flores were destroyed or damaged. The earthquake remains one of the most devastating seismic events in the history of the Lesser Sunda Islands. Its importance today is not simply historical. It provides a real-world demonstration that the Flores Thrust can generate an earthquake large enough to produce both severe ground shaking and a devastating local tsunami. When a magnitude 7.7 earthquake occurs again in the same broad tectonic environment, scientists and emergency agencies naturally examine the new rupture through the lens of that earlier catastrophe. Yet the latest earthquake should not be described as a repeat of 1992. The two events occurred at different locations, and their rupture characteristics may prove substantially different. The 1992 earthquake occurred farther east relative to the current epicenter and had a reported depth around 28 kilometers, or 17 miles, according to United States Geological Survey information. The current event has been placed much shallower, around 10 kilometers, or 6 miles. Their fault rupture areas, slip distributions, directions of propagation, and seafloor deformation also need to be determined independently. Comparing them is scientifically useful, but assuming they were mechanically identical would go beyond the available evidence. That distinction becomes especially important when considering tsunami generation. A shallow earthquake can be highly destructive without producing a massive tsunami if most of its movement occurs in a way that produces limited vertical displacement of the seabed. Conversely, an earthquake that appears moderate by magnitude can sometimes produce unexpectedly large waves if submarine landslides or unusual fault geometry become involved. The 1992 earthquake is an example of this complexity. Its tsunami was disproportionately destructive for an earthquake of its magnitude, and offshore landslides have been proposed as one explanation for the enormous run-up observed at certain locations. The August event therefore needs to be studied not just as a 7.7 earthquake, but as a complete earthquake-tsunami system. The Flores Thrust itself is much larger than the rupture associated with any single earthquake. Geological mapping and seismic studies have identified a long back arc fault system extending through portions of the Lesser Sunda Islands. Its western and eastern sections show different structural characteristics, and the fault is not a single uniform plane. Researchers have identified segments, ramps, folds, and blind thrust structures that develop through the complicated evolution of the region. Some sections reach the seafloor, while others remain buried beneath sediment and volcanic material. This structural complexity means that earthquakes can behave differently from one segment to another, making detailed geological mapping essential for understanding future seismic and tsunami hazards. A blind thrust is particularly important in this region because it can produce significant deformation without creating an obvious crack at the surface. The fault may terminate underground while the rocks above it fold and rise as movement continues. During a major earthquake, that buried structure can still produce vertical deformation of the seabed or land surface. Communities, therefore, cannot rely on visible fault scarps to determine where danger exists. The absence of a dramatic surface break does not mean the fault is inactive. In the Flores back arc system, earthquake locations, seismic reflection profiles, and geological observations all contribute to reconstructing these hidden structures. The August earthquake will provide another valuable data set for refining those models. The regional tectonic forces responsible for the Flores Thrust operate continuously. Australia is moving northward relative to the Sunda Banda region, but the motion is not absorbed at a single fault. Instead, the crust responds through a network of structures. Some deformation occurs at the main subduction boundary. Some occurs through back arc thrusting. Other movement takes place along strike slip faults and smaller structures. This partitioning of deformation is common in complicated plate boundary zones. Indonesia is an extreme example because several major tectonic domains converge across a relatively small geographic area. The result is a landscape where earthquakes, volcanoes, uplift, subsidence, and landslides are all connected to the same long-term tectonic engine. Flores itself provides visible evidence of that engine. The island is volcanic and mountainous, and its landscape has been shaped by repeated uplift, erosion, volcanic activity, and faulting. Sedimentary layers have been folded by compression, while marine terraces record changes in land elevation over geological time. Offshore, the seafloor contains structures associated with active thrusting and deformation. These features do not appear overnight. They accumulate over thousands and millions of years. A major earthquake is simply the sudden expression of a process that is otherwise almost invisible to human observers. The August 14 event released in seconds or minutes what the tectonic system had been storing through slow deformation for years, decades, and centuries. The earthquake also generated a substantial aftershock sequence. More than 200 aftershocks were reported during the early response period, including events above magnitude 6. Such activity is normal after an earthquake of magnitude 7.7 because the main rupture changes the stress field around the fault. Rocks adjacent to the ruptured section may experience increased or decreased stress, and some nearby faults can respond through smaller earthquakes. Aftershocks usually decrease in frequency over time, although strong aftershocks can continue for days, weeks, or longer. Their locations are scientifically valuable because they can outline the dimensions of the main rupture and reveal which parts of the fault system were activated. The aftershock map may ultimately become one of the most revealing pieces of evidence from the August event. If earthquakes align along a dipping plane, scientists can use that geometry to estimate the orientation of the ruptured fault. If the sequence spreads across several structures, it could indicate that the earthquake involved a more complicated network of faults. Depth variations can reveal whether the rupture stayed within a particular crustal layer or propagated into deeper structures. The pattern may also show where the main rupture stopped. These details matter because a fault that breaks in segments does not necessarily behave in the same way during every earthquake. Understanding those boundaries is fundamental to assessing long-term seismic hazard. For now, the immediate priority remains recovery and safety. Damaged buildings must be inspected. Landslides must be cleared carefully. Communities cut off by road failures need assistance. Aftershocks must continue to be monitored. Coastal residents must remain alert to official tsunami information and natural warning signs. Emergency agencies need accurate assessments of isolated communities. Scientists need time to process the enormous quantity of data generated by the earthquake. The full consequences will take time to document because some of the most remote areas may be among the hardest to reach. Early casualty figures, therefore, should be treated as provisional until authorities complete their surveys. The longer-term priority is understanding what the earthquake has revealed about the fault. Every major rupture provides a rare opportunity to examine a geological system under real conditions. The August earthquake has effectively exposed another portion of the Flores Thrust's behavior. Its seismic waves traveled through the crust, its fault movement changed the shape of the land and seafloor, its aftershocks illuminated surrounding structures, and its tsunami response provided another test of regional warning systems. Scientists can now use that information to improve models of future earthquakes and tsunamis. The goal is not to predict the exact date of the next disaster. The goal is to understand the hazard well enough to reduce its consequences. Nearly 34 years after the catastrophe of 1992, the Flores Thrust has moved again with a magnitude 7.7 earthquake. That number is close enough to the earlier event to demand comparison, yet different enough in depth, location, and tsunami behavior to remind scientists that every rupture must be studied on its own terms. The latest earthquake has already demonstrated the continuing hazard posed by the Flores back arc system. It has also provided researchers with a modern dataset that may reveal more about the hidden architecture of the fault than was possible 3 decades ago. The fault has spoken again, and the scientific record is now listening more closely than ever.